Look at the empty space around you right now. The air between your eyes and this screen. It feels like nothing is there. Scientists just found the strongest evidence, yet that nothing has been lying to you for 90 years. This story has a bit of everything. A genius physicist. A 90-year-old unsolved mystery. A dead star spinning faster than you can blink. Wrapped in a magnetic field that could erase your credit cards from over 100,000 miles away. And an international team of scientists who spent months pointing some of the most sensitive instruments ever built at one single point in the sky, hoping the universe would finally hand over an answer. By the end of this video, you're going to understand something that took physicists 9 decades. A dead star with a magnetic field beyond anything humans can build. And a small army of telescopes spread across 3 continents to almost prove. And I say almost, because even the scientists who found it are not fully agreeing yet on exactly what it means. Stick with me, because that disagreement is honestly the best part of this story. This is a tale of how one of the strangest predictions in all of physics may have finally, after 90 years, come true. Here's a question that sounds too simple to matter. What is empty space actually made of? For most of human history, the answer was easy. Empty space is made of nothing. You take a box. You pump every last atom of air out of it. You block out every photon of light. And what is left is a true vacuum. A perfect, silent, do-nothing nothing. Then quantum mechanics showed up in the early 1900s and ruined that nice, simple idea. According to quantum theory, a true vacuum is never actually calm. It is closer to a pot of water, sitting right at the edge of boiling. From a distance, the surface looks smooth and still. But zoom in close enough and you would see tiny bubbles constantly forming and popping, over and over, faster than you could ever count them. Empty space does something similar, just on a scale so small and so fast that we cannot see it with our eyes or catch it with ordinary equipment. Pairs of particles are constantly flickering into existence out of nothing, then vanishing again almost instantly. Physicists call these virtual particles. An electron and its opposite twin, called a positron, blink into being for an unimaginably short moment, then cancel each other back out, as if the universe is borrowing a tiny bit of energy and paying it right back before anyone notices. This is not some fringe idea that one weird scientist came up with. It is baked into the core of quantum physics, and scientists have already proven pieces of it in the lab. Take 2 ordinary metal plates and place them extremely close together, with a true vacuum in between, and something strange happens. The plates get pulled toward each other, ever so slightly, for no reason that makes sense under classical physics. Nothing is pushing them. Nothing is touching them. What is happening is that those flickering virtual particles get squeezed out from the tiny gap between the plates more than they are on the outside, creating a real, measurable force out of what is supposed to be nothing. Scientists call this the Casimir effect, and it has been measured again and again since it was first confirmed. So this fizzing, bubbling vacuum is not a wild guess dreamed up to sound interesting. It is a measured, repeatable fact of nature, and it is already reshaping how physicists think about what nothing actually means. Empty space, according to everything we understand about the universe, is a churning, fizzing sea of particles winking in and out of reality, everywhere all the time, including in the space around you right now. Here is where the story gets interesting. What happens if you take that fizzing, bubbling vacuum and drop it into a magnetic field so powerful it defies imagination? According to a nearly 90-year-old piece of math, something very strange should happen. Light passing through that patch of space should start behaving differently depending on which direction it is pointing. Empty space should start acting less like nothing and more like a filter. Scientists call this vacuum birefringence. And it is the reason we need to talk about one of the most violent objects in the entire universe. You have probably heard the name Werner Heisenberg before, even if you cannot remember why. He is one of the founding fathers of quantum mechanics, the same field of science that gave us computer chips, lasers, and MRI machines. Back in the 1920s, he helped write the rulebook for how the universe behaves at its smallest scales. You might actually know him best for a different, even more famous idea, called the uncertainty principle. In simple terms, it says certain pairs of properties, like exactly where a particle is and exactly how fast it is moving, can never both be known with perfect precision at the same time. Push that idea a little further, and you get something wild. It also means a universe can briefly break its own energy rules, as long as it pays the debt back fast enough. Borrow a tiny bit of energy from nothing, spend it creating a pair of particles, and pay the loan back in full by having those particles disappear again before anyone can catch the universe in the act. That loophole is exactly what allows virtual particles to exist in the first place, and it came from the same physicist who would later go looking for what happens to them under an extreme magnetic field. In 1936, working with his student Hans Euler, Heisenberg took that rule book and asked a bold question. What would happen to empty space itself if you expose it to an unbelievably strong magnetic field? To understand their answer, you need a quick detour into something called Birefringence, which sounds complicated, but is actually something you may have already seen with your own eyes. Certain crystals, like a mineral called calcite, do something odd to light. Shine a single beam through one, and it splits into two separate beams, each traveling at a slightly different speed depending on which direction it is vibrating. That is why looking through a clear piece of calcite can make whatever is behind it look doubled. Polarized sunglasses use a related trick. They are built to block light vibrating in one direction, while letting light vibrating in another direction pass straight through, which is how they cut down on glare bouncing off water or a car windshield. Normal empty space does not do anything like this. Light of any direction moves through a true vacuum at the exact same speed, no matter which way it is oriented. Nothing to see here, literally. But Heisenberg and Euler's math said that was only true because we had never seen a strong enough magnetic field. Crank the field up high enough, they argued, and all of those flickering virtual particles stop appearing randomly. They start lining up, snapping into formation along the direction of the magnetic field, like iron filings around a bar magnet. And once they line up, the vacuum stops being featureless. It develops something like a grain, the same way a plank would have a grain running through it. Light traveling along that grain moves slightly differently than light traveling across it. Empty space, under a strong enough magnetic field, should start acting like one of those calcite crystals. There was just one enormous problem. The magnetic field required to see this effect was so extreme that no laboratory on Earth could ever hope to produce it. Heisenberg and Euler had written down a testable prediction that nobody on the planet had any way to actually test. So it sat there, a single, lonely paragraph buried in physics textbooks for generation after generation. Quantum electrodynamics, the broader theory that grew out of this kind of work, would go on to become one of the most precisely tested ideas in the history of science. Its predictions about how electrons behave have been checked against experiments and found accurate to something like 12 decimal places. 12. That is an almost unbelievable level of precision for any scientific theory. But every one of those triumphs happen in the world of weak magnetic fields, the kind we can actually build. The strong field world that Heisenberg and Euler described stayed completely unchecked for nearly 90 years, not because anyone doubted the math, but because nobody could reach it. It was a cold case with no way to gather evidence. That changed when scientists turned their attention away from Earth entirely and looked instead toward the most magnetic objects in the known universe. To test Heisenberg's idea, scientists needed a magnetic field at least 100 million times stronger than anything humans have ever built in a lab. Since building one was never going to happen, they went looking for one instead. And the universe, it turns out, had already built exactly what they needed. When a massive star runs out of fuel, it does not just fade away quietly. It collapses in on itself in a violent supernova explosion. And if the leftover core is just the right mass, gravity crushes it down so hard that protons and electrons get smashed together into neutrons. What is left behind is called a neutron star, an object so dense that ordinary matter as we know it stops making sense. Every so often, maybe around 1 in 10 times, something even stranger happens. The collapsing core is left spinning unbelievably fast, while its magnetic field gets wound up and amplified to levels that should not be physically possible. The result is called a magnetar. It is still technically a neutron star, but with magnetic field so far beyond normal that it earns its own name entirely. You might be wondering how a magnetar compares to a black hole, since both get thrown around as the most extreme things in the universe. They are cousins, not siblings. Both start out as a collapsing core of a dying, exploding star. If that core is massive enough, gravity wins completely and crushes it down into a black hole, a point where not even light can escape. If the core is a little lighter, gravity gets stopped by the sheer pressure of neutrons refusing to be squeezed any further, and what is left behind is a neutron star instead, one that technically still has a surface, still gives off light, and in rare cases, becomes a magnetar. A magnetar is not a black hole. It might just be the most extreme object in the universe that is not one, and unlike a black hole, we can actually watch what is happening on and around it. Scientists did not always know magnetars existed. The first hint arrived on a single day in March of 1979, when spacecraft near Venus and the Sun were suddenly slammed by an enormous burst of gamma radiation, overwhelming the detectors in a fraction of a second. Nobody knew what had caused it. It took over a decade of theoretical work before physicists Robert Duncan and Christopher Thompson worked out the underlying physics in 1992 and gave this new class of object its name, magnetar, short for magnetic star. Then, on a day in December 2004, one particular magnetar on the far side of our galaxy showed the world exactly how much power these objects are hiding. In about 1/5 of a second, it released more energy than our sun produces in roughly 250,000 years. The burst was so intense that it saturated detectors on satellites scattered across our entire solar system, bounced measurable radiation off the surface of the moon, and briefly disturbed the upper layers of Earth's own atmosphere, all from a source tens of thousands of light years away. That single event is the kind of power hiding inside the word magnetar. Here is what you are actually dealing with when you look at a magnetar. A ball of matter roughly 20 kilometers across, about the size of a city, yet somehow packed with more mass than our entire sun. So dense that a chunk the size of a sugar cube will weigh somewhere around 1 billion tons back here on Earth, spinning around multiple times every second, sometimes completing a full rotation in about the time it takes you to blink, wrapped in a magnetic field that can be trillions of times stronger than the one protecting our planet. Strong enough that, according to scientists who study these things, a magnetar placed halfway between the Earth and the Moon could wipe every credit card on the planet clean. Get close enough to one of these things, and ordinary chemistry basically stops working. The magnetic field is strong enough to distort the shape of atoms themselves, squeezing them into thin, needle-like versions of what they normally look like. Nobody has ever gotten close to a real magnetar and lived to describe it, and given what that field would do on the way in, nobody ever will. Compare that to the strongest magnet doctors ever put you inside. A hospital MRI machine typically produces a field of somewhere between 0.5 Tesla and 3 Tesla. The very strongest research magnets built anywhere on Earth top out somewhere around 60 to 100 Tesla. And those are dangerous, temperamental machines that engineers handle with extreme care. A magnetar can produce a field billions to trillions of times stronger than that MRI machine, all wrapped around an object smaller than most cities. Magnetars are also genuinely rare. Out of the roughly 3,000 neutron stars astronomers have identified in our galaxy, only about 30 are confirmed magnetars. They tend to live fast and settle down relatively quickly on cosmic timescales, which is part why we do not find more of them. Once scientists realized what magnetars were capable of, the connection to Heisenberg's 90-year-old prediction became obvious. If any object in the universe could crank empty space up to the point where it started acting like a crystal, it would be one of these. Nature had built the laboratory that humans never could. Having the right kind of object out there is not the same as actually catching it in the act. Pointing a telescope at a magnetar and hoping to see vacuum birefringence is a bit like trying to photograph a very specific, very faint fingerprint from many light years away, while ruling out every other possible explanation for what you are seeing. It was not just astronomers pointing telescopes at the sky, either. Back on Earth, one dedicated team built a laboratory experiment called PVLAS, using powerful magnets and a laser beam, hoping to catch the same effect happening right there in a room with them. That project has now been running for roughly 25 years. 25 years of careful, patient, painstaking measurement, using some of the strongest and steadiest magnetic fields humans can safely generate. And even after all that time and effort, no laboratory on Earth has come anywhere close to a field even a fraction as strong as what a magnetar carries naturally, without even trying. It is a genuinely humbling reminder of the gap between what humans can build and what the universe casually produces in its sleep. The first real astronomical attempt came in 2016. A team led by astronomer Roberto Magnani used a very large telescope, a giant observatory in Chile, to study the light coming from a nearby neutron star. This particular star was not quite a full magnetar, more like a slightly less extreme cousin, located roughly 400 light-years from Earth as part of a small, quietly nicknamed group called the Magnificent Seven. These 7 neutron stars do not flash with regular radio pulses the way most known neutron stars do. Instead, scientists find them by their faint, steady glow of leftover heat in X-rays, the last trace of warmth from a star that stopped making its own energy a very long time ago. They are also some of the faintest, hardest targets in the entire sky to study in visible light, which is exactly why measuring anything from one of them at all counted as a real technical achievement. The team measured the polarization of that faint visible light and found something exciting. Around 16% of it was polarized in a specific way, more than you would expect if empty space were just doing nothing at all. One of the researchers on the project, Dr. Vincenzo Testa, put the achievement simply, saying it was, quote, "This is the faintest object for which polarization has ever been measured," end quote. It was a genuinely exciting result, but it was not proof. The confidence level was not strong enough to rule out other explanations, and a handful of unlikely but possible alternative scenarios could still account for what they saw. It was a scientific equivalent of a blurry photograph of a fingerprint, promising, tantalizing, but not enough to close the case. The team's own conclusion pointed toward the obvious next step. If a moderately magnetic neutron star produced a hint this strong, then a true magnetar, with a field up to 100 times more powerful, should produce a signal that was impossible to miss. The problem was finding the right one. Magnetars are rare to begin with, and most of them are faint or hard to observe in the kind of detail this experiment would require. Worse, even a genuinely powerful magnetar is not automatically useful for this test. The geometry matters enormously. If the magnetic field is not lined up in a favorable way relative to Earth, the light passing through it from different angles gets blurred and scrambled, and any Birefringence signal gets muddy beyond recognition. Scientists needed a magnetar that was not just strong, but positioned almost perfectly for observation. For years, nobody had found one that fit the bill convincingly enough to settle the argument once and for all. That is where our story properly begins. Fast forward to a research team that included Dr. Marcus Lower at Swinburne University of Technology in Australia, working alongside an international group of collaborators spread across multiple countries. Their target was a magnetar cataloged under the name 1E1547, or 1547 for short, because nobody wants to say that whole designation out loud more than once. It is one of roughly 30 confirmed magnetars known to exist in our entire galaxy. This particular magnetar completes a full spin around its own axis roughly once every 2 seconds. Picture a dead star, 20 kilometers wide, spinning around completely in about the time it takes to say the word magnetar out loud. It is also known for being genuinely dramatic even by magnetar standards, having previously produced sudden violent outbursts of energy that caught astronomers' attention in the first place. To catch a signal this subtle, one telescope was never going to be enough. The team needed several instruments working together, almost like a relay team passing a baton. NASA's Imaging X-ray Polarimetry Explorer, known as IXPE, launched in December 2021 from Kennedy Space Center in Florida. It is the very first satellite ever built purely to measure the polarization of X-rays coming from objects in space, essentially a pair of enormous polarized sunglasses pointed permanently at the cosmos. Nicer, an X-ray telescope bolted to the outside of the International Space Station, providing extra eyes on the same target. Murriyang, a giant 64-meter dish radio telescope, sitting out in the Australian outback. This same dish beamed humanity's first pictures of the Apollo 11 moon landing to television screens around the world back in 1969, and in 2020, it was given traditional name Murriyang by Wiradjuri elders, meaning skyward, the home of a creator's spirit in Wiradjuri dreaming, connecting the oldest astronomy on this continent to some of the newest. Observations were also supported by a radio observatory in South Africa, adding yet another set of eyes from yet another continent. Dr. Lower personally collected radio data, using Murriyang, and the team crunched the numbers using Swinburne's own supercomputer, appropriately enough named Gargu Tindabeek. Here is roughly how a satellite even manages to measure something as strange as the polarization of an X-ray. Inside IXPE, incoming X-rays strike a special gas sealed inside a detector. When an X-ray hits a gas particle, it knocks loose a tiny charged particle called an electron, and that electron shoots off in a direction connected to the way the original X-ray was vibrating. By recording the direction thousands upon thousands of these tiny electron tracks fly off in, and building up a pattern from all of them together, scientists can work backward and figure out how polarized the original X-ray light actually was. It is a bit like studying the splash pattern of raindrops hitting a window to figure out which direction the wind was blowing, done over and over, one X-ray at a time, until a clear pattern finally emerges from the noise. Picture the scale of this for a second. A satellite orbiting Earth. A telescope riding the International Space Station. A giant dish in the Australian bush that once connected the whole planet to a moon landing. Another observatory on a different continent entirely. All of them pointed at overlapping moments at one small, spinning, furiously magnetic dead star, hunting for a signal that might not even be there. Most of the core observations were gathered around March and April of 2025, kicking off months of careful analysis. This was not luck. This was a deliberate, coordinated hunt for a very specific kind of ghost. Before the team could even start looking for vacuum birefringence in the X-ray data, they needed to answer a more basic question. Was this particular magnetar actually pointed at Earth in a useful way? Here is the issue. As a magnetar spins, the direction its magnetic field points relative to us keeps changing, sweeping around like a lighthouse beam. If you are viewing that lighthouse from an awkward angle, the beam only grazes past you at certain moments, and the light you catch gets mixed together from many different angles through the magnetic field, blurring out any clean signal. But if you happen to be looking almost straight down the axis the light is sweeping around, you get a much cleaner, much more direct view. To figure out which situation they were in, the team studied how the radio waves coming from 1547 changed their polarization direction as the star completed each spin. By carefully mapping those changes, they could work out the actual geometry of the system, the angle of the magnetic poles compared to the spin axis, and the angle of the whole setup compared to Earth's line of sight. What they found was remarkable. The magnetic axis and the spin axis of this magnetar turned out to be almost perfectly lined up with each other. On top of that, the entire system happened to be oriented, so we are viewing it almost exactly pole-on, essentially looking straight down the barrel of the magnetic field, rather than off to one side. Think of it like looking directly into a flashlight, instead of catching its beam from across a dark room. A direct, aligned view gives you the cleanest possible signal, with the least amount of blurring and interference. Out of all the magnetars scattered across our galaxy, this one happened to be sitting in about as close to a perfect viewing position as scientists could hope for. It was not something the team engineered. It was a pure stroke of cosmic luck, discovered only after carefully studying the data. With the geometry confirmed, the team finally had what they needed. A magnetar with an extreme enough magnetic field, aimed at Earth in about the best possible way, with multiple telescopes already watching. All that was left was to see what the X-rays were actually doing. This is a part of the story where 90 years of waiting either pays off or falls apart. When the team analyzed the X-ray light collected by IXPE, they found polarization levels far beyond anything expected from ordinary explanations. Here is what the numbers actually look like. Averaged across the star's full spin, close to half of the X-ray light was polarized in a specific, consistent direction. At lower energy X-rays, closer to the magnetar's own surface heat glow, that number climbed to around 65%. At certain precise moments during its spin, polarization spiked as high as 80%. To put that in perspective, other magnetars studied with the exact same telescope typically show far more modest polarization levels. This particular signal came in at roughly 3 times higher than comparable sources, an unusually dramatic result that immediately stood out from everything else IXPE had measured before. But a huge number by itself is not proof of vacuum birefringence. It could, in theory, come from other physical processes happening around a magnetar. This is where the second clue became just as important as the first. The direction the X-ray light was polarized and was not random. It lined up with the direction of the magnetic field, and it matched the exact pattern the team had already mapped out using the radio wave observations from Murriyang. Think of it like two separate witnesses to the same event, questioned completely independently, who both described the same story down to the smallest detail. The radio waves pointed one way. The X-rays pointed the same way. Both matched what Heisenberg and Euler's math predicted should happen if the virtual particles in the vacuum really were lining up with the magnetic field, exactly as described nearly 90 years earlier. Dr. Lohr explained the underlying idea, simply. Because of the magnetic field's incredible strength, those flickering virtual particles become aligned with the direction the field is pointing, and by tracking how both the radio waves and the X-rays behaved as the Magnetar spun, the team found that the alignment of this Magnetar's magnetic and rotational poles was about as ideal as it gets for catching vacuum birefringence in the act. Two independent signals, collected by completely different instruments, using completely different methods, pointing toward the exact same conclusion. That is about as strong as observational evidence gets in astrophysics. It is not a smoking gun sitting on a table with fingerprints all over it, but it is close. Here is the part most headlines will skip over, and it is honestly the most important part of the whole story. Not every scientist studying this data is fully convinced yet. Getting the exact same measurement is not the same as agreeing on what caused it. A separate team of researchers, looking at the same numbers, argued that if the geometry of the system is even slightly different than the first analysis assumed, then the sky-high polarization numbers alone might not be quite enough by themselves to prove vacuum birefringence is definitely what is happening. Both groups agree on what IXPE actually measured. They simply disagree, for now, on which physical explanation fits those numbers best. This is not a scandal, and it is not a failure. This is genuinely what good science looks like, while it is happening in real time, rather than after it has already been neatly wrapped up for a textbook. Excitement, careful measurement, and healthy disagreement, all happening at once. So what happens next? More observation time pointed at the same Magnetar, and others like it. More advanced computer simulations, capable of ruling out competing explanations with much greater precision. Dr. Lohr himself put it best, saying that with future data and updated simulations, the team may finally be able to, quote, complete the quest started by Heisenberg nearly 90 years ago, end quote. If that quest really does get completed, the payoff is enormous. It would mean directly confirming, for the first time, that quantum electrodynamics holds up even in the most extreme magnetic fields in existence, something physicists have only ever been able to assume, never actually check. It would hand scientists a brand new tool for probing the strangest, most extreme corners of quantum theory, using Magnetar scattered across the galaxy as natural laboratories no human could ever build. And it would mean that a single paragraph written by two physicists in 1936, describing something nobody on Earth could test at the time, turned out to be exactly right. Think back to the empty space around you right now, the same space we started with at the very beginning of this video. It is still following the exact same rules the space around that distant Magnetar follows. The only difference is scale. You will never see your coffee cup do anything strange, because the field around it is nowhere close to strong enough. But scale that field up by a factor of 100 million, wrap it around a dead star 20 kilometers wide, and apparently nothing stops behaving like nothing at all. Subscribe so you are still here when this 90-year-old case finally, officially, gets closed for good.